Good afternoon, everybody. Today, I want to begin a new topic, which is to discuss gases and liquids. Okay, so this is going to bring us closer to liquid crystals in that these are systems of molecules moving around. And so we can start to see how to apply the statistical mechanics description to something like that. And to begin with the easiest case, I want to talk today about the ideal gas. Okay? And so the point of the ideal gas, the thing that makes it ideal, is that there is a very low density. And because of that, we can neglect the interactions between molecules. So the notion is then that we have a box, right? And a bunch of molecules are flying around in the box. So I'll make my box be some volume size L by L by L, right? So the volume V is L cubed. And inside are a whole bunch of molecules, which are all flying around. Something like this, okay? And so each molecule at any moment in time has some position, R1, R2, R3. And each molecule at any moment in time has a velocity or momentum. And the way people usually set this up is in terms of momentum. Okay, so I'll label that there's a momentum, P1 and P2 and P3. So these molecules are flying around. They're bouncing off the walls. They're not necessarily bouncing off each other, right? Because we're neglecting the interactions between the molecules, and bouncing off each other is a kind of interaction, okay? So we don't have that, but they are bouncing off the walls. And so the positions and momenta are changing in time. All right, and so now we want to apply statistical mechanics to a system like this, okay? And so, as with the case with the Ising magnet, we want to describe all the states and classify the microstates into macrostates and think about what's the free energy of each macrostate. All right, so that's what I'm going to try to set up today. Okay, and so today is going to be mostly math to set things up, and then we'll get to some results maybe at the end of this class or the beginning of the next. All right, so first of all, if we want to talk about states, right, we have to say, whoops, wrong pen. What's a state? So for the Ising model, it was pretty clear what was a state because we just have a list of spins, okay? And each of those spins has two possibilities. It could be up or it can be down. And so if we want to describe a state in the Ising model, we just need to say, make a list of all the spins from number 1 to number 10 to the 23rd. And for each spin, we say, is it up or is it down? Here, the analogous thing has to be for a list of the molecules. Okay? So we could say that there are capital N molecules, and we need to make a list of the positions and momenta of these molecules. Okay? So we could make a big list and say for molecule number 1, there's a position for 1 and a momentum. Okay, and then for molecule number 2, there's a position and a momentum. Dot, 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 right? Going up to the last one. So for molecule number N, maybe 10 to the 23rd, right? There's a position and a momentum. So that is to say, for each molecule, we are going to be specifying 6 numbers, right? So for the position, that's 3 components, right? X, Y, and Z. For the momentum, that's 3 components, X, Y, and Z. Okay? So that makes 6 just for molecule number 1. Okay? Another 6 for molecule number 2, etc. So in total, there are 6n degrees of freedom. Now, one way that you might visualize all these degrees of freedom is through something called phase space. That is a plot of all the different, with axes for all the different degrees of freedom. Okay? So we could make a big plot where we say this axis is X for particle number 1. And this axis is P sub X for particle number 1. Okay? And so that's 2 out of the 6n degrees of freedom. Okay. Now we have to imagine that there are a lot more axes. So there's an axis for Y for particle number 1, an axis for Z for particle number 1, an axis for PY for number 1, PZ for number 1, maybe for X of number 2, right, et cetera, et cetera. Now, this is not very practical in practice, right? I mean, if we have 10 to the 23rd particles, we will have 6 times 10 to the 23rd axes. I'm not going to be able to draw all those things on my 2-dimensional whiteboard. But conceptually, you could imagine, maybe I could draw such a thing, right? And so, you know, if you imagine such a construction, then a particular state is a point in phase space. Let's say it's that point right there. Okay? And so, in principle, you could look at that point and read off what is X and Y and Z for particle number 1, and PX and PY and PZ for particle number 1, and then the same for number 2 and number 3, etc. Okay. So this is the idea of phase space, and then a state is a point in phase space. Okay. I should emphasize, this is not a phase diagram, right? A phase diagram, like we talked about last week, that's a completely different concept. This is a different use of the word phase. Okay, so this then is a way to visualize all the states of the system. Now, we might want to talk about what's the energy, right? So for each state, there is some energy of a state. That energy is the sum of the kinetic energy plus the potential energy. The potential energy in general could be interactions between particles. And interaction of a particle with some external field. For example, the interaction of a particle with the box, right? Maybe there's some potential energy associated with walls of the box, right? Or another example that I'll get into on Wednesday would be an interaction of a particle with gravity. Okay, now, because we have the ideal gas, that means we are neglecting the interactions between particles. Let's forget about those things for now. Okay. For the moment, I will also choose to consider a system where there's no interactions of particles with an external field either. Okay, so no gravity, no box potential, anything like that. Okay, so in that case, the energy of a state is just kinetic energy. Okay. So now we know how to express kinetic energy. Okay, so if we want the total kinetic energy that is associated with a state, okay? So energy that's a function of R1, P1, R2, P2, etc. Right? This is the sum of the kinetic energies of all the individual molecules. So it is a sum over molecules. So a sum from I equals 1 to n, right? So I is the molecule number, right? Ranging from 1 to n. And then the kinetic energy of a single molecule is the momentum squared over 2m. You'll recognize that momentum squared over 2m, that's the same thing as 1/2 m vi squared, right? So if you're working with velocity, you say 1/2 mv squared, but if you're working with momentum, it's p squared over 2m. And I should say, of course, this is a P sub I, not P sub 1. Okay, so P sub I, the momentum of particle number I. Right? And M is the mass. And I'm going to suppose all the particles, all the molecules have the same mass. Okay, so this is the energy, and with all the simplifying assumptions that I've made, this is now independent of the positions. So independent of R1, R2, right, all those positions, right? So it only depends on the momenta. Okay, now we know what to do, right, in doing statistical mechanics calculations. Right? So for statistical mechanics calculations, we want to say things like, what's the probability of a state? Okay? So the probability of some state P2, etc. Right? That is e to the minus energy over kT divided by the partition function. Right? This is just like what we were talking about way back at the beginning of the course.
Excuse me.
Please.
I think this the expression on the right hand side should be multiplied by the volume of the phase space dR1 d.
Hang on a second. I will get to more things in just a second. Okay, so first, let me talk about what is the partition function. Now, we know from the stuff that we did earlier in the semester, right, that the partition function is a sum over all the states of the exponential, e to the minus energy of the state divided by kT. Now, here we get to a subtle issue, which is related to what Cheng was asking about a minute ago. So I'm going to leave a question mark here. Is this right? It's almost right, but I got to fix it up. Okay. Now we get to a subtle issue, which is we don't really have a list of states, right? It's not a countable list, right? With the Ising model, right? We could say, there's a state where this guy's up and everything's down, right? And then we can say this guy's up and this guy's up and then all the rest are down, right? In principle, we could make a list of all the possible states and add up some countable set of terms. Okay? Here, however, there isn't a list. There's a continuous family of states, right? That is, the position could be there, right? Anywhere. The velocity could be this, right? It's a continuous variation. So for that reason, we can't just write a sum. We have to make an integral over all the possible positions and all the possible momenta of the states. Because an integral is the continuous version of a sum. Okay, so we might say, let's try something like this. Okay, I'll keep a question mark. Let's make an integral over all the components of R1 and all the components of P1. And then we'll integrate over all the components of R2 and all the components of P2. And then we'll keep going. And we'll integrate over all the components of Rn and all the components of Pn. Then the thing that we integrate in this gigantic integral is going to be the exponential of minus the energy as a function of all this stuff, R1, P1, etc., right, divided by KT. Okay. So this then would be a generalization of the summation for the partition function that we did before. You can recognize, right, in this notation, right, the integral d cubed R1, right? This means dx1, dy1, dz1. And integral over P1 means dpx1, dpy1, dpz1. Okay. So in this integral, I am integrating over 6 variables for each molecule. Okay. So if they're 10 to the 23rd molecules, I'm integrating over 6 times 10 to the 23rd variables. Okay, so I put this question mark there. Is this right? Well, it's almost right. Almost right. There are 2 little problems that I have to fix. Problem number 1 is that the units are wrong. You know, a partition function is supposed to be dimensionless. Right? Z should be dimensionless because it's a sum of these exponential terms, the e to the minus energy over kT, right? And so the exponential e to the minus energy over kT is dimensionless. If you have a sum of a whole bunch of dimensionless things, it's still dimensionless, right? However, this expression right here is not dimensionless, right? It has dimensions of 3 factors of position and 3 factors of position and 3 factors of momentum for each molecule, all right? But it has dimensions, whoops, it has dimensions of length times momentum, 3 factors of that for each molecule, so to the 3n power. So, in order to make it dimensionless, I should divide by something which has units of length times momentum to the 3n power. Now, luckily, there is a fundamental physical constant which has the right units of length times momentum, and that is Planck's constant. Right, so Planck's constant H has units of length times momentum. You know that because it goes in the Heisenberg uncertainty principle, right? And so a Heisenberg uncertainty principle says that the uncertainty in length times the uncertainty in momentum is related to something like Planck's constant. Okay? So we could divide by Planck's constant to the 3n power. Okay, so I'm going to fix up this expression by dividing by that. Okay, so, ooh, I can do it with my lasso. I'll copy it. Let's do it. If I lasso this thing. Whoops. Copy. Does it work? So paste. Ooh, it sort of works. There it goes. Okay, so I will divide by 1 over h to the 3n. Okay, now that gets the right units. Okay. There is actually a fundamental reason. There is a quantum mechanics reason why we should be dividing by h to the 3n. And that has to do with, you know, if you go back to the area, the picture of phase space. I said before that a state is a point in phase space. But when you think about quantum mechanics, that's not exactly right, okay? So a state, if I say a state is a mathematical point in phase space, that means that I know the position exactly precisely, and I know the momentum exactly precisely. But the Heisenberg principle says, no, you can't do that, right? That there's always going to be some uncertainty in position related to the uncertainty in momentum. So that means I can't really say that a state is a mathematical point in phase space. It has to be that a state is like a little fuzzy region in phase space. To say, you know, the momentum and the position are in this box, but I don't know exactly where in the box they are. Okay? And so based on the uncertainty principle, I would say the volume of the box associated with each state should be something like Planck's constant to the 3n power. Okay, so that makes a good reason to divide by h to the 3n. Question? Please go ahead.
I mean, are we discussing about Maxwell's Boltzmann's distribution or something else here?
Yes, the Maxwell-Boltzmann distribution.
And in the original derivation of Maxwell-Boltzmann distribution, there is no any quantum mechanics. We do not need to consider these things. We can
that's true, and indeed, it doesn't really matter, right? And you will see in the calculations coming up that the factor of Planck's constant will drop out, right? And so the predictions are not going to depend on the numerical value of Planck's constant. But still, it is necessary to get all the formalism to work right and to get all the formalism to have the right units.
I mean, in Maxwell-Boltzmann distributions, we can just simply consider like n is equal to n naught exponential minus energy divided by kBt, and if we integrate both sides with respect to this phase space, then we can easily get that one. I mean, there is
yes, that's right, and I will eliminate it in most cases, but it comes in certain odd places like the absolute value of the entropy.
Okay.
And so I'm including it here, even though I recognize that it won't matter in those cases. All right, so this fixes up one of the problems, okay? The other problem that needs to be fixed, right, is that the particles are indistinguishable. That is, the particles are not like pool balls where each one is marked with a number, right? And so really they are fundamentally the same thing. Okay, so that means that if you have a state with particle 1 that's here, so this is R1 and P1, and then here is R2 and P2, okay? And then I'll draw another one over here, where this is R2 and P2, and here is R1 and P1, right? So far I'm counting things as if these are two different states. But in fact, because the particles are indistinguishable, these things are really the same state, right? Really, all we can say is that there's a particle here moving that way, and there's a particle here moving that way, and there's no way to tell that this is particle 1 and this is particle 2, as opposed to vice versa. Okay? So that means that these things are really the same state. There and there, okay? But so far in the counting that I have made, I have overcounted, right? I have counted these things as if they are two different states. And moreover, if there are 3 particles, then there are 3 factorial ways to rearrange the counting. So I've overcounted by 3 factorial. Right? If there are n particles, then there are n factorial permutations of the labels, which means that I have overcounted the states by n factorial. Okay? So I can compensate for that problem by dividing by n factorial. So that means that that's one other thing I need to fix, right? So I'll lasso by equation again. And copy. And then here. Paste. Oh, that's so much fun. Okay, so I will, I'll fix things up then by dividing by n factorial. So this now is the partition function that I have repaired, okay? Okay, this now is the correct partition function, okay, which has all the repairs taken care of. So this then is an expression for the partition function of the ideal gas? Well, it is at least an integral to give us the partition function, but we still need to actually do the integral. Okay, so let's do it. Okay, so we can say this is now the 1 over n factorial h to the 3n, and I have my integral over position and momentum for number 1, and the same for number 2, dot, 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 okay. And then I need to take the exponential of the energy that we already talked about. So the exponential of minus the sum over particles, 1 to n, of pi squared over 2 mkt. Okay. Now, let's do this integral. Okay. So the first thing that you can see is that nothing depends on positions. Right? With all the simplifying assumptions, does not depend on positions, right? With all the simplifying assumptions that I have made, there's nothing in the integral that depends on positions, okay? So for each of the position integrals, I'm integrating something simple, okay? So when I integrate over x for particle number 1, right, I'm integrating from 0 to L, right? And likewise, when I'm integrating over y for particle number 1, factor of L, okay? So I get 3 factors of L for each particle. Or equivalently, I get 1 factor of L cubed, or 1 factor of volume for each particle. So I'll just factor that out. So I get volume to the n now divided by n factorial h to the 3n. And now I've done all the position integrals. So I just have to do the momentum integrals. d cubed p1, d cubed p2, etc. Right? And now the thing that I'm integrating is the exponential of a sum. Luckily, we know that the exponential of a sum factorizes into the product of the individual exponentials. Okay? So this is the exponential of minus p1 squared over 2mkt times the exponential of minus p2 squared over 2mkt times the same for particle 3, the same for particle 4, etc. Now, to keep on simplifying, I can put the thing that depends on momentum number 1 together with the integral over momentum number 1, and the same for number 2, and the same for number 3, and so forth. Okay, so this is v to the n factorial h to the 3n. So it's the integral over the 3 components of momentum number 1 of the exponential minus p1 squared over 2mkt. And that's it. That's all that depends on the momentum of number one. Now I have the same thing for particle number two. P2 squared over 2m kt. And then the same thing for particle 3 and particle 4 and so forth. Right? Then we notice that all the particles are the same as each other, right? So this integral is just the same as this integral and every other integral in the list. So I have an integral for each particle that are all the same. So I can just write it as the integral over any old momentum, exponential of minus p squared over 2m kt. And all this is just raised to the n power, okay, where n is the number of particles.
Can you, I'm sorry, can you explain that step one more time, how you go from the integral of the multiplying of each integral over each different exponential momentum, and then how you change them basically to all be the same momentum?
Sure. It's because I'm using the way that an exponential factorizes, right? And so you know that when you have the exponential of a sum, it's the product of exponentials, right? And so this exponential of a sum is the product of an exponential for particle 1, an exponential for particle 2, times an exponential for particle 3, etc. Okay. Now, I'm just going to rearrange the factors, right? So I'll take this factor and put it next to the P1 integral, right? And I'll take this factor and put it next to the P2 integral, okay? And the P3 factor and put it next to the P3 integral, and so forth, okay? Then I say, ooh, good luck, right? Because these integrals don't depend on each other, right? So the P1 integral is just an integral I can do by itself that doesn't have anything to do with the P2 integral, right? And likewise, the P2 is an integral I can do by itself, and it doesn't have anything to do with any of the others, right? So, you know, this is not normally true for multiple integrals, right? Normally, when you have a multiple integral, the integration over one variable involves the other variables, right? That makes multiple integrals hard, right? But in this case, with exceptional good luck, right, the integrals become independent. And so I can then write the parentheses there and say each integral is an integral that I can do separately without thinking about the others. Okay. Now, once I've done the parentheses, then I can say, oh, well, the thing in these parentheses is the same as the thing in these parentheses, right? All that's different is the label on the momentum, right? Whether it's labeled as momentum 1 or momentum 2. So I can label it as just any old momentum, or I could just say it's momentum 1 or call it anything, right? But now it's n copies of the same integral. Is that good?
Yeah. It was just the second to the last step that I was confused on.
Right, because it normally doesn't work for multiple integrals, but it works for this multiple integral because of the independence of the energy, right? That the energy of particle 1 doesn't have anything to do with the energy of particle 2, right? And so it is a special feature of the ideal gas that will not work so well later when we have a non-ideal gas. Okay, so but to complete the story for the ideal gas, okay, we can keep on simplifying, and we get Z is this now V to the N over N factorial H to the 3N. And then we have something to the N power. And the thing to the N power is an integral dpx, dpy, dpz, all right, of the exponential of minus px squared plus py squared plus pz squared over 2m kt. We can actually use this separation trick once again, right, for the three components of momentum, right? So we could say this is v to the n over n factorial h to the 3n. And now we have an integral dpx of e to the minus px squared over 2m kt. And then we have the same thing for py. And then we have the same thing for pz. So this whole thing cubed and then to the n power. Okay? So now this is just one integral raised to the 3n power. And this is an integral over all the possible values of px, which could go from minus infinity up to infinity. Okay, so now this is just an ordinary one-dimensional integral, which we can do using our favorite method. We could put it into Mathematica or look it up in an integral table or use an online calculator. I'll skip that and just skip ahead to the answer, okay? And so the answer, this is v to the n, n factorial over h to the 3n, and this integral now gives us 2 pi mass kt raised to the to the 1/2, right? The square root of this thing raised to the 3n power. So our answer for the partition function now, I guess the shortest way to write it would be to put all these things to the nth power together. And so we have volume, we have 2 pi m kt to the 3/2 over Planck's constant cubed. Okay, so this then is our result for the partition function of the ideal gas. Now, one thing we can do with this is to calculate the free energy of the ideal gas, because you know that the style of working with things is to work with the free energy. That's the way I'm pushing in this course. Okay? So suppose we want to get the free energy. Okay? Well, I want to take the log of the partition function. So here, I'll copy this again. So the free energy that will be negative kT times the log of z, of the partition function. So negative kt times the log of this thing I'm going to paste. No. Paste here. Yeah, times the log of this. Okay, so, and then simplifying the log, right? We know that the log of a product of things is the sum of the logs, right? And we know that the log of this thing raised to the n power is n times the log of that thing, right? So the free energy becomes minus kT. And so let's see, we have n times the log of what's in the square brackets right there. Okay, so n log v 2 pi m kt to the 3/2 over h cubed. And then minus, so that cancels the minus in front, so plus kt log n factorial. And now, same as we did with the Ising model, I can use Stirling's formula to simplify that. So the log of n factorial is approximately equal to n log n minus n. Okay, and so I will put that into this expression. Okay, so what do I get? Right. Well, let's see. This is the free energy. Lasso. Okay, and so in place of log n factorial, I want n log n minus n. So n log n minus k t n. Okay, and now let's take all this stuff and I'll stick it all inside the same log. So it's ktn log v 2 pi m kt to the 3/2 over h cubed. Okay, and then if I have this term and I want to stick it inside the log, so then I'm, whoops, wrong pen, I'm dividing by n, like that, inside the log. And now I have this term and I want to stick it inside the log. And so that means that I multiply by e inside the log, and because the log of e is 1. And this is it. Okay, so this is the free energy of the ideal gas in a volume V. So ideal gas, and so that would be n molecules in a volume V. So one thing I can point out about this expression is that it is extensive. That is, if I change V to 2V and N to 2N, so it's twice as many molecules in twice the volume, then you get twice the free energy. That is as it should be. By comparison, if you have twice as many molecules, but you don't have twice the volume, you keep the same volume, then the free energy changes in a more complicated way. But that's okay. It should change in a more complicated way because then you have a denser system. It's really a different kind of system. And so you wouldn't expect to get just double the free energy. All right. So this is our story about an ideal gas in a fixed volume. Right? And I am out of time. I will have to stop here. And in the next class, I'm going to build on this result and say, what if you have an ideal gas in a variable volume under fixed pressure? And how do you deal with that? Okay, so I will stop here and I'll be glad to answer any questions. Please, Bajai.
Jonathan, I mean, what is the difference between kinetic energy, free energy? I mean, so how free energy comes? It will come from kinetic energy or potential energy or thermodynamic energy or all possible energies.
The free energy comes from energy and entropy, right? Okay. And so the energy here is only kinetic energy. There's no potential energy so far in the calculation. Right? So it is coming from a combination of kinetic energy and entropy.
Okay, so only in the thermodynamic system we will have free energy. That's
correct. Only in the thermodynamic system do you have free energy.
And we should have system of particles to have free energy. I mean, if I have only one particle in space, then I will not have any free energy.
That's correct, yes. Yes. Okay. Now, it doesn't have to be particles. There could be fields, right? I mean, we'll talk later in the semester about fields instead of particles, right? And there's still free energy there. That's right. So if I were teaching a course about thermodynamics, right, I would then start teaching other things about the ideal gas, right? We could calculate things like what's the energy and the entropy separately for the ideal gas. And indeed, that's worked out in the textbook, right? And so we could calculate something like what is the average energy of particle 1. Okay. So that would be the average of the energy of number 1. Okay. So we can work that out with the usual way of doing averages, right? That it's a sum over all the states of the thing you want to average in that state times the probability of that value, right? Of that state, right? So in this case, the sum turns into an integral, right? So we would have 1 over n factorial h to the 3n integral integral P1. The same for R2, the same for P2. Okay, and then the thing that we want to average is P1 squared over 2m. And then the probability is the exponential of minus energy over kT. Now, this is an integral that we can do, all right? And most of the integral is exactly the same as what I already did for the partition function. Oh, and excuse me, I forgot a very important part, which is the probability is this stuff divided by the partition function. I forgot that normalization, okay? We can do this, right? And I will just skip to the answer. Okay? And the answer, I mean, you guys can do this for practice, and if you have questions, we can talk about it, right? But the answer, if you do this, is not 1/2, it's 3/2 kT, right? That is the energy that you get this way depends on temperature. Right? We could then say, what's the average total energy? That average total energy will be 3/2 kT for particle 1. The same thing for particle 2, the same thing for particle 3, right? So multiply by the number of particles. So 3/2 nKT. So this is the average energy of the ideal gas. Right? Now we could say the free energy. So this is coming back to your question, Vijaya. The free energy is the average energy minus temperature times entropy. Okay? So if we know the free energy and we know the average energy, we could get out the entropy of the ideal gas. Right? So the entropy of the ideal gas would be this average energy minus the free energy divided by temperature. Okay? And yeah, I mean, that works. And so that makes, you know, a slightly messy expression for the entropy, but it totally works. Well, so this is, you know, meant to answer your question that, you know, you can get out specific predictions for all these thermodynamic properties coming from the statistical mechanics formalism.